Hi, this is Dave Canabran. Today we'll be talking about the functionalities and capabilities of the Statistica Enterprise platform. Then we'll also look into some of the newer features of our most recent release, version 13.2. We'll start with some of the key differentiators, such as the end-to-end solution, how to create visualization dashboards within the analytic workflows, the ability to do real-time process monitoring and monitor everything from input data to model performances, and how we can leverage open source tools and languages, specifically talking about the integration with R and Python. And then we'll focus on the Citizen Data Scientist UI, which is the ability to leverage the power of advanced analytic workflows using simple web interfaces. Then we'll look into the app marketplaces such as Algorithmia, Appervita. Then I'll walk you through an example of a distributed network graph analytics. Then we can dig deeper into big data analytics, specifically in database analytics in Spark using H2O integration, and also in database analytics in relational databases such as Oracle, SQL Server, Teradata. And then we'll look at deep learning. And then I'll walk you through a typical modeling workflow using the example dataset that was provided, which was the airline data, and walk you through everything from data acquisition to data aggregation, and then modeling, model evaluation, model management, how to publish certain templates, and finally automation and governance. Let's now talk about some of the key differentiators. As I said, one of the biggest differentiators is the ability to create a complete end-to-end solution in a single workflow, which can then be templatized and reused. So here, let's start with the end user's perspective, and then we can work our way backwards. So I'm going to start with the visualization dashboard. So here you'll see that we have an integrated visualization dashboard within the analytics workflow, which allows us to point to multiple data sources and then create visual dashboards on top of those data sets. This is a typical BI type dashboard which we can use to slice and dice data. So here you can see that we have broken down the delay, the average delay, as well as the total number of delays by origin and destination airports. And like any BI tool, we can very easily filter by specific subsets. You can drill down. It's highly interactive and very user friendly. So here we are looking at the probability of cancellation or specifically delay greater than 15 minutes by airline. We can even create different kinds of calendar widgets. And more importantly, these dashboards can also be used to interpret the results of advanced analytics. And we will come back to that in a second. The other differentiator is around real-time process monitoring. So here you see we have a dashboard that has been set up to monitor multiple processes and parameters in real time. So here if you see everything is green, that means it's okay. If something is yellow, we know that there's a connectivity issue. And here, as you just saw, if something turns red, we know that there's some issue with it. And you can see that we can create hierarchically nested dashboards. So here I have it initially broken down by airport, and within each airport, we can have it broken down by airline. And then we can drill down into individual airlines and identify why certain airlines have a higher predicted delay and so on. So I can now interactively drill down into this specific chart and identify what's going on. And as I said before, this is not just for real-time process monitoring, but it can also be used for model management, where we are monitoring the accuracy of predictive analytic models. Next, let's look at how to leverage open source tools and languages. So we saw that this is a typical workflow where we have data coming in from multiple data sources. We go through aggregation and we're using some native Statistica methods to do feature selection. But let's say, for example, we wanted to use a Python package to do feature selection. So in this case, let's say I want to use a random forest regressor to do feature selection. We could very easily start coding our own Python script right here. Or even better, since we have complete integration with Statistica Enterprise, which is the centralized repository, we can very well point to an existing template. So here you'll see that I already have a Python script, which I can now just point to. As you can see, it supports multiple versions of Python as well as different languages such as R, SVB, C#, and so on. We can now run this node and look at the results of feature selection using a random forest regressor from Python. So here are the results of the random forest model. It gives us an importance metric which can now be used to identify our top factors, which can then be used for modeling. The power of analytics is truly realized when it's not just contained within data scientists, but when we can take it to the masses. Or in other words, when we can enable business users to leverage the power of advanced analytics using simple and easy to use web interfaces. Let's say this is a comprehensive analytics workflow developed by a data scientist. We can now use the designer view to parameterize these different nodes and expose only certain parameters. So in this case, to keep it simple, we're exposing just the fit type for the scatter plots as well as the variable selection for the feature selection node. To the end user, this is just another template in the web interface. So here they can now run this parameterized workflow template, and all they will see are the different options that we expose. So here we gave them the ability to choose fit type for the scatter plot and the variable selection for the modeling. So we know based on experience that hour of day is an important factor in modeling. So in this case, just to show you how easy it is for the citizen data scientist to play around with these different templates. So we'll select everything other than hour of day and run the models. So here we have the results based on the options that we selected. So we looked at the scatter plot, and as we go down, we can look at the feature selection as well as the modeling from the booster tree models that we selected. So if we look at the final lift chart, it's a lift of 1.45, which is not great, but we know that we didn't select one of the top predictors, which is hour of day. So we can now go back and rerun this parameterized workspace with a few differences. So let's say we want to change the fit type to linear, and under feature selection, let's now select variable 82, which is hour of day. So here we can see the scatter plot with the linear fit. And if we scroll down, by the way, we can see that the hour of day is clearly a very good indicator. And when we scroll down, we can now look at the lift of 2.5 from the booster tree models, which is significantly better. So as a citizen data scientist or a business user, we have used just the web interface to actually go in and change the model and interactively play around with the different parameterizations that have been exposed to us. One of the key differentiators is around collective intelligence. As the user community for advanced analytics grows, it's critical to help data scientists and citizen data scientists alike to scale their efforts and deliver value quicker. By integrating Statistica with application and algorithm marketplaces, we make it easier for our users to tap into the wisdom of crowds and leverage a wider community of experts. As you will see, Statistica is fully integrated with H2O, Apervita, Algorithmia, as well as R and Python, which allows users to leverage our open architecture to access a wide variety of marketplaces directly from within a validated platform. If you look at this ribbon bar, you'll see the different app marketplaces that we support. We use RESTful APIs to connect to Algorithmia. So here you can see that we can provide the API key and also specify where the data resides, whether it's within Algorithmia or locally, and then run any kind of model. And the same goes for Apervita, which is mainly used in healthcare. And similarly, we can do the same with Azure ML as well. But more importantly, we can also create custom nodes and custom scripts with C Sharp or Kotlin, Python packages, or R packages, or even create your own. We can now publish this as a protected workspace within Statistic Enterprise, which is our centralized repository, where it now becomes a template which allows us to monitor it, manage it, automate it, schedule it, and so on. And like everything within Statistica Enterprise, we can now assign access permissions. So here we can specify exactly who has access to what template. And once you have this analytic template, You can now execute this from anywhere very easily. So now you'll see that all we have to do is bring in an execute workspace node, attach it to the new data, and then point it to this published protected workspace that we just created. So here, all we're doing is pointing it to that particular template. So with a few clicks, we can now bring in multiple models from various app marketplaces and execute it on new data very easily. For in-database analytics, it's very important we look at it from an end user's perspective. So what you're looking at here is a typical analytic workflow where we query data, bring it into the application server, and then run analytics. For in-database, we can pretty much mimic the exact same workflow. So let's start by pointing it to the data config, which is the bridge to your data source. And by the way, we can support multiple data sources like SQL Server, Oracle, Teradata, MySQL, and Apache Hive. Once we have this connection, we can now run in database descriptive statistics, and we can, pretty much throw in all variables and get all different kinds of descriptive statistics, except the processing happens in database. And similarly, you can run in database correlation matrices, or you could even do in database feature selection. So we know this is especially important when you want to identify the top factors before you throw it into modeling. So in this case, let's say we want to identify which of our factors are important in helping us predict those airlines which have a delay greater than 15 minutes. We can do that all in database. And once we have that, we can now feed that into advanced analytic models such as CHADE or logistic regression, multiple regression, lasso regression, even clustering if needed. So there are a lot of different methods that we can use. So here we are using a logistic regression method. And we can now run this analytics. And as I said, even though to the end user, the designing process looks exactly the same, most of the processing happens in database. So we bring back only the aggregated results. So the advantages of doing this is improved operations as we can leverage the performance of the database server, improved reliability, especially in the case of slow intermittent network connections, improved security because we are not carrying over all of the raw data over the network, and this in turn reduces the risk of security breaches. And since we bring back only the relevant data in the aggregated form over the network, it significantly improves performance as well. And it's relatively easier to set up because Statistica does not require you to install anything specific on the database, unlike most other platforms out there. There is the obvious caveat around resources because anytime you're running advanced analytics on your database, it might interfere with primary database operations. So we have to be careful about that. This is an example of an H2O flow within Statistica. Here we are using all airline data for 2007 from an Amazon S3 blob storage. While it's running, I just wanted to talk about the analytic technologies, both hardware and software, that are evolving very rapidly and the large number of highly specialized and useful algorithms, platforms, and scripting languages that are available as either open source or from commercial providers. The issue that is facing the market is how do we leverage these technologies and solutions without building out specialized analytics silos of data scientists within the organization, where some are using R, others Python, or MLlib, or H2O. This is where Statistica comes in, as we support big data analytics natively via in-database processing, but also provide a single coherent platform that supports various commercial as well as open source big data algorithm providers or app marketplaces such as Azure ML, Aprovita, Algorithmia, and also H2O. I also want to emphasize that Statistica integrates with H2O as well as H2O plus Spark, or sparkling water as it's called, which extends the high performance computing capabilities of Statistica and uses Spark for efficient, scalable, in memory distributed big data analytics. By the way, here are the results on all data. We strongly believe that the capabilities of a platform should never be constrained by what a vendor or open source project decided to support. Instead, Statistica allows users to leverage whatever works best for the problem at hand or for the organization in general and bring it into a validated environment with version control, model management, automated recalibration, and so on. Statistica integrates with Microsoft's Computational Network Toolkit to support deep learning. For this case, we're going to take the typical MNIST database. We're going to take 60,000 fixed size images and use it as training for handwritten digit recognition. So here you'll see that we are now going through a web service to get those images, and we're going to use 60,000 images for training and the remaining, which is about 10,000 images for testing. And when we run this, initially what it does is it goes through this web service and brings back those images and converts them into a flat file of pixel densities. Once we have that file, we can now apply any kind of modeling on it. In this case, we are running a traditional random forest classification model, and then we are testing it against the holdout sample of 10,000 images. And if we look at the results of our random forest classification model, it does okay and comes back with an accuracy of about 78%. It is not bad, but there is clearly room for improvement. So now we can run the exact same problem on a deep convolutional net. It takes about a couple minutes to run, but if we look at the results, you'll see that on the holdout sample of about 10,000 images, it does significantly better, and now we get an accuracy of about 99% for each handwritten digit. This is the power of deep learning. In this case specifically, it's a feed-forward convolutional neural network. Another key differentiator is edge analytics. Let's take an IoT use case specifically around predictive maintenance for airport body scanners. So airport body scanners are expensive machines with a lot of different parts that could potentially fail. So our goal here was to identify in real time which particular parts have a higher likelihood of failure and make sure that they are notified ahead of time so that they could have replacements ready to go. So that way we can ensure minimum backlog. So here we are looking at various factors like temperature sensors, ambient temperature, pressure, humidity, and the number of cycles per minute. And we're using advanced analytic methods behind the scenes to predict the risk of failure for a particular part, which is what you see at the bottom. And here you'll see that a spike here shows that there is a very high likelihood that a particular part is going to fail. So as you can see, there are a lot of advanced analytic methods behind the scenes. This is a typical workflow where we have multiple different models for predictive maintenance. And as we run these models, the most important thing is we can now take these models and deploy them as various different types of codes. So here you can see that we can now deploy these models as PMML, C, C++, C Sharp, SQL stored procedures, Teradata rules, or as Java. Once we have identified the type of code that we want, we can now push this model to a centralized repository, which is what we call Statistica Enterprise. You can either deploy or update an existing model, and here we can now specify the model, update it, and this now becomes as part of the centralized repository. Each model has a unique ID, and once we identify that ID and type of code that we want to bring it back as, we can now access these models via the enterprise API that we have now made available. So here I'm looking at a particular model and I want to bring the underlying deployment code in Java. So here we can bring it back as Java code, or we could even bring it back as C sharp, or if needed, even as PMML. Once we've built the model and identified a particular language that we want to push it out as and made it as part of enterprise, we can now go to a model transportation layer. In this case, we are using Boomi, where it now connects to all these different data sources and also has a custom connector for Statistica, which basically uses the enterprise OData service to point to this specific enterprise metadata table space where I have saved those models as Java code, and I can now go through those list of models that we have already deployed and just point to any model that we want to use as part of the Boomi flow. This Boomi flow can now be pushed as a Java virtual machine to the edge or a gateway. And finally, you can now even write the results to a database. Statistica Network Analytics allows users to visualize and analyze the associations and relationships between various entities and actors. As we like to say, once you have a hammer, everything looks like a nail. Similarly, once you have these capabilities, we can now visualize any kind of data as a network. So in this case, we're taking the airline data with the weather factors that we brought in. And here you'll see that we can now do any kind of filtering or even clustering. So in this case specifically, we are trying to cluster the different airports by the common weather factors and patterns and weighted by the delay that is caused by these unique weather patterns. So here you can identify which airports are specifically affected by strong rain or which airports are more likely to be affected by fog or sleet or freezing rain and so on. And here you'll see that it's a nice interactive and visual tool which you can play around with. But more importantly, we can fully customize this and make it look however we want. We can change everything from the size to the icons to the color and so on. We can also do some very interesting anomaly detection, which is using unsupervised learning methods to identify clear anomalies. In this case, we are trying to identify the origin airports themselves that clearly stand out with respect to these weather patterns and the delays caused by them. Interestingly, Chicago O'Hare stands out, and we know that is because it is affected by multiple extreme weathers and it also results in numerous delays. So that's a very interesting finding. And again, there are a lot of different anomalies that we can now drill down into and identify what's going on. So that's the network analytics, where you can not only do filtering and clustering and anomaly detection, but also do scoring for predictive analytic methods using an interactive and intuitive tool. Also, the results of these various analyses can be brought into the Statistica workspace environment. Here, we can use a network analytics node and connect to the server, and this now enables users to look at the various networks that were created. So in this case, we'll choose the airport weather patterns network, and we can now select the different models that were run. So let's bring back the results of the anomaly detection and specify our actor class. So we can now look at the results of our anomaly detection model specifically for origins and which of these were classified as anomalies. If needed, we could also select only a subset of suspicious actors. This level of integration allows users the power to use a distributed graph database for processing, thin client for an interactive UI, and the workspaces for further processing and reporting of results. For the modeling flow, we took the example data that was provided, which is the airline data, and broke it down into chunks and dispersed it across multiple data sources. So here you'll see that some of it is on a blob storage on Amazon S3, and then we have some of it coming in from a flat file, And then here, there's some coming in from a relational database, some coming in from a data lake on Hadoop. And the openness of Statistica allows for us to bring in data from various different sources, including third-party web services. In this case, we're specifically bringing back data from the METAR weather services. METAR stands for Meteorological Terminal Aviation Routine, which is a very comprehensive weather service and which is what most aviation pilots use. And this is what we will be using for most of our modeling as well. And then we also are connecting to a web service to bring back holiday information. Specifically, we are trying to identify if national holidays make a difference to airline delays. And we can also connect to different kinds of geolocation and geocoding packages out there to bring back the latitudes and longitudes of each origin and destination airport and see if we can somehow use that in modeling or at least use it for better presentation of results in the final visualization dashboard. All of these different data sources can very easily be aligned and aggregated within Statistica. All these different data sources are now available to the query builder as data tables. So we can now very easily align and aggregate data within the graphical query builder that you're looking at here. And there's a very comprehensive tool which allows us to create queries with just drag and drops. We can even specify the type of join, whether you want a left outer join, inner join, and whatnot. You can specify groupings, you can specify criteria or where clauses, you can do subqueries, expressions, all of this within the graphical query builder. And here you'll see that as we click on this, it'll generate the query for us, which makes it really easy to align and aggregate data. Once we have the data, we can now run it through the data health check summary, which is what I call the one-stop shop for data understanding. Here, all we have to do is just select all variables and run it through the typical checks, which is checking for sparseness, checking for outliers, checking for invariance, and checking for redundancy. But the best part is not only does it run just a diagnostic report, but we can also configure it in such a way that it also applies the most appropriate statistical methods to cleanse the data. This is the result from the data health check summary. So here you'll see that it automatically breaks it down to continuous and categorical variables. It identifies specific categorical variables with more than 100 levels. It identifies the sparseness of each variable, and it also gives us an outlier detection summary. So you can go through this, or you could even look at it from a variable standpoint. So here are all the variables, and those that have some kind of issue is highlighted in red. And here you'll see that this one has redundancy, these ones have outlier problems, these ones have invariance. So with just a couple clicks, we can take care of a big chunk of the data understanding and data pre-processing steps, which, as we know, are the most time-consuming parts of any project. We saw earlier how to analyze all data using in-database. We'll now perform a by-airport analysis because it's likely that different airports have different drivers. We'll start with Chicago O'Hare. So let me now run this whole workflow in real time, and we can see as it goes through all these different steps. So typically it queries the data from all those different data sources, and we can go through aligning and aggregating, but here it's coming in from a simple data table. And then we subsetted only those airlines that originated from Chicago O'Hare. And then we ran it through automated variable selection, which is identifying which of these factors are the most important to help us predict airline delays. And then we're going through a typical process of breaking it down into training and testing data. And then we are running multiple different types of data mining models, specifically boosted classification trees. And then we are running it through automated neural networks and chain methods. And as we have already seen, we could very easily open this up and bring in all different kinds of models, whether they are R packages or Python modules, or pushing this to algorithmia and scoring it there, or even scoring it on Azure ML or even bringing in some deep learning methods. Ideally, deep learning is better suited for ImageNet classification and speech recognition, but we do have deep learning methods. So here you'll see that we could throw in a deep learning classifier and build a deep neural net. Anyways, here you'll see that the modeling is now finished. So what we can do is we can now go through the results and compare these models. So here we can look at the gains chart, we can look at the lift chart, or we could look at the ROC curves, or if it makes sense, we could even assign a profit and a cost and look at profit cost charts. Let me also dig deeper into some of these results here. So here you can look at the importance plot, and it's very interesting that a lot of the different metadata that we were talking about initially for both the origin and the destination airport seems to be very important. So we can break it down by these different factors. And interestingly, the hour of day when a particular flight is scheduled to depart seems to be a very interesting fact. And this we're breaking it down by whether or not the delay is going to be greater than 15 minutes. So going through this, we can identify a lot of different factors. For example, the relative humidity of the origin airport is an interesting factor, which seems to make a significant difference to whether or not there's going to be a delay of greater than 15 minutes. Similarly, the temperature in Fahrenheit seems to make a difference as well, and so does the dew point index. The comprehensiveness of Statistica allows us to slice and dice data in all different forms. And here you'll see that we are breaking it down by unique carriers, uh, all of which originated from Chicago O'Hare. And here you'll see that Delta seems to be doing significantly better than all of the other airlines. If we go further and break it down by specific airports, which we know are some of the most traveled to from Chicago, we can still see that Delta Airlines has only a 20% probability of having a delay of greater than 15 minutes, whereas someone like United has a 33% probability, American Airlines has a 30% probability, and so on. Obviously, all of these results are made available to the end user or business user via simple, intuitive, and easy to use visual dashboards. Here we can see the same results as a visual dashboard. So here this is the result from the feature selection or the automated variable selection that we're talking about. So we can see that the hour of day or time, as well as the relative humidity, the altitude, the temperature, the dew point index, all of the different factors that we saw are highlighted here. And we can look at hour of day and see how that makes a difference. And by the way, what we're looking at here is the prediction from advanced analytic models. And we could even use this as a what if scenario generator. We can interact with these different charts. And as we interact with them, you'll see that the numbers here, which is basically the risk of delay, is being updated in real time. While we have created these models only for flights from Chicago O'Hare, we could very easily create a model for all airports. So here you'll see that rather than go through the subset, I'm connecting it to the original data, and we can do what we call by group analyses. So here, instead of bringing or running it only for Chicago, we could very easily say run a by group for every single origin airport. And what this will do is this will now run the same model, but it'll run it for different subsets of data, in this case, for each origin airport. Once we have built an analytic workflow, we can very easily deploy it to Statistica Enterprise with just a couple clicks. So here I'm deploying it as a new object in Statistica. And here again, you'll see that this is fully validated, meaning it keeps track of who makes what change when. And we can even assign user access permissions so that we know exactly who has access to what templates. The advantage of deploying these models to a centralized repository like Statistica Enterprise is that it now allows users to automate, schedule, and run on demand, and more importantly, monitor and manage all these different modeling templates. So let's say we want to do some champion challenger modeling. Here, for this particular data set, we know that the neural network seems to work the best. But before we push this to production, we need to know if this is better than the current champion. In order to do that, we can now bring in the champion model and compare it against the existing neural network model. Here you can see that we can just go in and load the PMML from the centralized repository. And here we have the champion, which is currently in production. And we are now going to compare that against the neural network model that we just created. So here we can see that the neural network model that we just built actually does better than the champion that is in production. So if we now want to push this model into production, we can very easily do that by going here and deploying this model into the centralized metadata repository, which is Statistica Enterprise, and updating an existing model, in this case, the champion. So we can now update that. But obviously, as I said, everything is validated and there's a very comprehensive audit control as well as a dynamic version control system behind the scenes. So it keeps track of all the changes that we make. Okay, while we are talking about champion challenger modeling, it's very important that we understand that there are various checks in place to make sure that unintended models do not make it into production. So that's exactly what we have here in this migration utility. And by the way, before we do that, I just wanted to show you the versions. So here you can actually go through all the different versions, identify how they're different, who made what change when, and you can look at different versions and you can compare them and so on. But as I was saying, once you have a champion in your development environment, which you think is the best model and you want to push it into production, we can use the migration utility where we can take any template, whether it's a data template or a dashboard template or an analysis template, and very easily push it into production with just a single click. But as I said, there are a lot of different options, such as only the latest approved versions can be transferred and so on. In this section, we'll be talking about a few topics that we couldn't touch upon in the previous sections. We'll start with real-time streaming analytics. So this is a very specific use case around accident data from NTSB. So this is real-time streaming data, and the green points denote accidents with no fatal injury, and the white points are accidents with fatal injuries. So we can now drill down in real time into these different points and we can look at in the street level information for this particular example. Another great example of real-time streaming data is an IoT use case like what we have here. So this is a manufacturing line with multiple processes and steps. At any given point in time, we can look at how each of these processes are doing and drill down into a specific process. So here we are drilling down into a specific process. And keep in mind that this is not just real-time monitoring, but rather we are looking at the predictions from advanced analytic models. In this specific case, it's a predictive maintenance model in real time. So these are predictions that are being made in real time. You can drill down into them, identify what went wrong, what the probable causes are, and so on. Another thing that we wanted to talk about was data transformation. So here we're using the same data set, which is the airline data set, but now we're adding a transformation node to create new derived variables specifically around the weather data. So as you can see, we can do multiple formulas within the transformation node and run it. And here we have our derived variables, which can now be used for further analytics. We also wanted to talk about conditional scoring logic using the rules engine. This is especially important because we can now build specific models for specific subsets of data. For this example, we took the relative humidity of the origin airport and broke it down by anything that's less than 55 and greater than 55. So if it's less than 55, we have a very specific model called low humidity model for that. And if it's greater than 55, then we have a high humidity model. We can now conditionally score multiple models based on specific criteria, and then bring back those results. So here you'll see that if humidity is less than 55, then you bring back results from your low humidity model. If not, you bring back the results from your high humidity model. The other thing was around offloading it to a server. So here you'll see that we can now log into the integrated Statistica Enterprise server and offload a complete workspace. This now goes and it's processed on the server, and it will automatically let us know when it has finished running, and we can say, okay, bring back not only the results but also the underlying data. And finally, I wanted to talk about text analytics. So here's a use case where we are looking at employee satisfaction surveys and we have open-ended responses. We are running text analytics on these responses, open-ended responses, and this will now bring back not only the raw frequencies of keywords based on those text, but also it brings back concepts based on what we call singular value decomposition. We can now use this for further analytics, specifically around sentiment analysis or topic classification. And you can now drill down into what percentage of these responses were positive, negative, highly positive, and so on. But the key differentiator is once you have the results and of text analytics, you can now use it for further analyses. Specifically, in this case, we're using it for attrition modeling and seeing if we can predict which employees are likely to leave the company based on their responses from previous years' employee satisfaction surveys. So we can use it for HR analytics. We are breaking it down by location. We can break it down by department, and we can also do topic classification, sentiment analysis, as I just mentioned. And using our interactive visualization dashboards, we can now very easily drill down into specific subsets. So here I'm looking at only those who are talking about right direction, and also they're talking about it in a very positive way, who think that the company is truly moving in the right direction. Earlier, we talked about how we can bring back geolocations and lat longs for further reporting as well as advanced analytics. So here I'll show you a quick demonstration of that. Here we have all different kinds of addresses. Sometimes it's a city name, or a city name with state, or it's a partial address, or it's a zip code, or it's an IP address, and so on. So we can take all of these, including airport codes, by the way, and run it through the geocoder node where you have a few options to specify what you want to do with it. So in this case, we are going to take the place names and bring back the latitudes and longitudes. If not, we could do it the other way around as well. So if you already have the lat longs, you can bring back the place and the name of the city and so on. So here we're going to run the geocoder node. In the results, you'll see that it brings back the lat long for all of these addresses. To summarize, we took the example dataset that was provided around airline delays, and we showed data access and how we can connect to multiple data sources, as well as we showed the geocoder node and how we can bring back the lat longs for further analytics and reporting. Then we talked about data pre-processing and data prep using the data blending and data transformations examples. We talked about how you can create new derived variables as well as use business logic using the rules engine, and how you could also use that for conditional scoring logic. And then we talked about data exploration, specifically using the data health check node, which is what we call the one-stop shop for data understanding and pre-processing. And we also showed a visual drill down capabilities using the visualization dashboards. And then we talked about automated feature selection, model building, model evaluation, model security and governance, specifically around auditing and versioning using the document management system. And then we showed model management and champion challenger testing. So then we talked about how, if you have a champion and it has gone through the approval process, how you can migrate that to a production environment using a model migration utility. Apart from these examples, we also talked about the flexibility, extensibility, and openness of the platform, emphasizing on collective intelligence and how we can access multiple app marketplaces such as Algorithmia, Aprovita, and Azure ML. Also, we talked about our integration with CNTK for deep learning. We then talked about the scalability and high performance computing capabilities using the H2O integration example. And then we talked about Statistica network analytics and how we can visualize and analyze the relationships and associations between multiple entities and actors. And finally, throughout this presentation, we've been talking about ease of use and how we can templatize and parameterize multiple analytic workflows and make it easier overall for the business user or the citizen data scientist to leverage the power of advanced analytics. Thank you.